So we've learned pretty much everything we're going to about proton NMR. Let's go ahead and move on to carbon NMR. Of course, we have to do the carbon 13 isotope because we need the odd number of protons in this, or neutrons in this case. So remember that carbon 12 makes up approximately 99% of all carbon, while carbon 13 is approximately 1%, right? And so you can see that our NMR active isotope is very small. And so we're going to get a very low amount of signal. And so what this results in is having to average a lot of scans. And so what this means, how proton NMR can be, you can get the NMR stuff in like a minute or two. This one will take hours. Usually when you do kind of carbon NMR, you set it up in the instrument and just let it run overnight, then come to the morning with your NMR. And this one actually doesn't have as much info as proton NMR, right? So it takes longer and not as much info, but it is still useful, especially when you get to more complex molecules. And so here's an example of a proton NMR of ethyl acetate here, right? So we've got our compound right here. First thing you'll notice is the chemical shift is much larger. It goes from 0 to 200 parts per million. This right here is the solvent peak, so you just go ahead and straight ignore that. And then it's kind of the same thing as proton NMR, right? This carbon is right on this oxygen, and so it's very de-shielded, and so it shows up all the way over here. While this carbon over here, carbon 4 over here, is very far away from our electronegative group, and so it shows in the more shielded region. So that part's the same. Something you'll notice that they're all just regular straight lines, so there's no splitting here. Right, there's no doublets, no triplets, no nothing like that. And another thing is that there's no integration. Right, so for example, in this compound right here, we have 4 unique carbons, and yet this carbon is like half the size of this one, but they both represent 1 carbon. And so with this no integration thing, you can't tell how many peaks a carbon how many carbons a peak represents. It might represent 1 carbon, it might represent 2, it might represent 3. You don't know. One big thing that helps though is symmetry. So for example, let's say you have C8H10, and so you have here 4 degrees of unsaturation. And so you're thinking, all right, I'm probably going to have a benzene, right? And this is something that you'll see quite often. And specifically here, we're going to say that we have dimethylbenzene. And so we have one of 3 ways to organize these methyl groups. And you can tell which one it is just by how many carbon peaks there are, right? This one will have, these 2 will show up as 1. These 2 carbons will show up as another peak. These 2 carbons will show up as another peak. And then finally, these 2 will show up as a 4th peak, right? So we've got 4 peaks there. Here we've got symmetry along the molecule in this direction. So we've got 1 carbon right there, 2 carbons right there, 3 carbons right there, 4th carbon, and then we've got a total of 5 different peaks. And then if we have this 1,4 substitution, we have symmetry down along this way. So these 2 are going to be, oh yeah, my bad. And then we also have symmetry this way, right? These 2 are going to be number 1. These are going to be number 2. And then all 4 of these will be number 3, right? So only 3 peaks. So again, by using symmetry and just taking a look at the carbon NMR, how many peaks there are, if you have a benzene, you can figure out what kind of substitution pattern you have if you have this di-substituted compound. Another very useful piece of carbon NMR is chemical shift. Similar to proton NMR, certain things will show up in certain regions. So we got like 50 over here, 100 over here, and then like 150 over here. So if you see something over here, above 150, below 220, or really close there, you have some kind of carbonyl, right? That's indicating this carbon right here, which we saw in our example of this ethyl acetate, right? It has a peak right here at Cooperate with me. At like 170-ish. If you go from 100 to 150, that's carbon-carbon double bonds or aromatic carbons. 50 to 100 is carbon either triply bonded to itself or attached to a nitrogen or an oxygen. And then 0 to 50 will be your regular sp3 hybridized carbons. And so similar to proton NMR, you should be able to look at a compound and predict what its carbon NMR looks like. So let's go ahead and take a look at this. And the questions we should be able to ask ourselves is how many signals are we going to have? And what kind of location will they be in, right? So the first thing you should notice is that we do have symmetry across this aromatic compound. And so we'll have one peak right here, two peaks right here, third peak right there, and then the fourth peak right there. And all four of these peaks should show up in our aromatic region. So they should all be about 150 to 200. Oh, my bad. 100 to 150. My bad. Next up, we have this carbon right here, right? That's our carbonyl carbon. That'll show up somewhere between 150 and 220. So that'll be peak number 5. And then we have peak number 6 and peak number 7 over here. That'll show up somewhere between 0 and 50. So we should see a total of 7 peaks from this compound.